Hey, this is DW, and I'm going to go through the exam today that we had last time. And I just wanted to walk through the key so that you can understand what I was doing or what I was looking for on the exam. So the vocabulary is pretty straightforward. If you'll just compare these uh, questions to the Quizlet, these are definitions straight from the Quizlet. For those of you who don't know how I run my class, I have the students generate the definition list on Quizlet as a study set, and then they can use all the Quizlet tools, or the matching and the flashcards. They can print exams for themselves and test themselves on the vocabulary. And then for 40% of the exam, I'll print up a 20-question vocabulary test, 10 multiple choice, and 10 fill in the blank. You can see the next page is the fill in the blank, so they look at the definition and have to supply the term. This is new for me in terms of my teaching career. It seems obvious to know the vocabulary, but I figured that that was something that the students would do on their own. It turns out that they don't typically. So I've added vocabulary to my exams. It'll get them a base of 40%, which is not really passing. So if they try to just do this basic level of knowledge and try to pass the course without moving up to the analysis section or the understanding and creativity sections, they wouldn't pass the course. But I find that if they do well on the vocabulary, then they have a shot at doing well on the questions that require more thinking. So you'll see those kinds of questions coming up. So this is, as it says up here, the remember and understanding section. This is vocabulary, and then we get to the questions that require them to apply and analyze the knowledge that they have. So let's zoom in a little bit. This top one is understanding the Grotrian diagram. So let's get my hand here. I can push this around. And so this is the apply and analyze section, otherwise known as problems. So these problems are similar to some things that we've done on the homework, but not exactly. So they need to understand what they did on the homework, and then they need to extend it a small amount to analyze the concepts that they learned in class, the concepts they've learned on the homework, and apply it to a slightly different situation. So here's a Grotrian diagram for helium, split between singlet and triplet combinations. We discussed this in class, so this is something that they should be able to repeat from class. We had all of the electron configurations given in class, and so they should be able to see that we start out with the 1s2 electron configuration for ground state helium, and then staying in that same orbital configuration, they can excite the electrons. And so if you move one of those electrons to a 2s orbital, it still has the term symbol of a singlet s, but now it's at a higher energy because one of those electrons is in the 2s orbital. It's still a singlet because the electrons can stay paired even if they're in different orbitals. So if we have a spin up and a spin down in the 1s orbital, that's 1s2, but if we excite one of those electrons into the 2s orbital, they're still spin paired, so it's still a singlet situation, but it's a higher energy because we have an electron that's not in the ground state. You can move it to a 3s and have an even higher energy. You can actually see up here that the ionization limit is set at 0, so the ionization energy for helium to pull one of those electrons all the way off of the atom is up here, so that's be slightly more than 24 electron volts. Okay, so let's go through this problem. So here are the things that were asked for this problem. They were to use arrows to show absorption and emission and label these transitions. So I was looking for an allowed singlet to singlet emission where an electron drops from a 4d to a 2p orbital. And so we're just moving one electron around with photons of light, either emitting a photon or absorbing a photon. And so here I'm looking for the electron that was in the 4d and moves to a 2p. So this lowest energy level in the d group is the electron in the 3d orbital and one in the 1s orbital. So that's the energy of that atom that has that electron configuration. The next level up would be a 1s 4d. So we want an emission line that goes from the 4d down to the 2p. And so that little arrow right there satisfies number 1. Problem number 2, the allowed singlet to singlet transition. So this is, again, singlet to singlet indicates we're on the left side of this Grotrian diagram. Singlet to singlet absorption, so an up arrow, where an electron jumps from a 2s to a 2p orbital. So this one here, number 2, is pointing to this arrow. So one electron in the 2s is going to the electron in the 2p. And these are the energy levels not of the 2s and the 2p orbital, but of the whole atom. So the whole atom with this configuration, 1s, 2s, has this energy, and the whole atom with a configuration of 1s, 2p has that energy. And really the net difference is that one electron has moved from the 2s to the 2p. So that would be the answer for number 2. Number 3, and just looking for any forbidden triplet to triplet emission. Show it with a dashed line. So it's emission, so it needs to be a down arrow. And any disallowed. So I drew this dashed line for number 3. It's going from an F to a P. Now why is that forbidden? Well, because it's jumping 2 columns. And so we have a change in the L quantum number of 2. And that takes 2 units of angular momentum, and light only has 1 unit of angular momentum. So jumping 2 columns is forbidden in these Grotrian diagrams. So going from a triplet F to a triplet P is forbidden. So draw it with a dashed line. Draw the arrow down here because it's emission. Then number 4, we want an allowed triplet to triplet absorption. So I don't specify which one. So I just grabbed these 2 levels. We're jumping 1 column to the right. So we're going from the 1s2s triplet to the 1s3p. So this is the 2p. The 1s3p triplet. And so that would be an allowed triplet to triplet absorption. And then finally, the shortest wavelength forbidden triplet to singlet emission transition. So there's lots of things going on. There's triplet to singlet, so I've got to cross this barrier in between triplet and singlet. That's forbidden. Okay. So I'm going to draw it with a dashed line. It's also asking for the shortest wavelength. Now, this is the typical one that's shown. We're going from the 1s2s down to the 1s squared orbital. But actually, I had a student draw one from this triplet F all the way down to the singlet S. And that would be forbidden as well, because we're jumping 3 columns and jumping from triplet to singlet. So, any combination coming from the right panel to the left panel would be fine for this answer. But this is also the longest one, and many students put like a transition between these 2, which are very close together. This tiny little energy difference is going to give us a long wavelength, and this huge energy difference is going to give us a short wavelength. And I think that was a concept that was missed by many students. Okay, and then finally this last one. What are the J quantum numbers for the triplet S energy levels? So that's this group here, the triplet S. So it's triplet, so that means the spins are unpaired. So S is equal to 1. Because the triplet means 2s plus 1 is equal to 3. Okay, that's the multiplicity. So a multiplicity of 3 comes from a net spin quantum number of 1. So the J values are L plus S going down to L minus S. So this is the maximum value, that's the minimum value. The maximum value, since it's an S term, L is equal to 0, S is equal to 1 because it's a triplet. And then 0 minus 1 is negative 1, but we take the absolute value, and that's the minimum. So the minimum is 1, the maximum is 1. So they only have 1 quantum number in this particular J value. J is equal to the set of 1. So this is what that term would be. All of these orbitals, all of these atoms in this column would have the term triplet S1. And so that's problem option number 1. Okay, problem option number 2. Determine the lowest energy electron configurations for all 8 columns in the helium Grotrian diagram. So here are 8 columns, and here are left to right all of the lowest energy electron configurations. So that just means this one's the lowest energy in this column, this one's the lowest energy in this column, there. So all of these bottom energy levels, what are the electron configurations for these? I show them up here on the Grotrian diagram, but I went ahead and wrote them here left to right. So 1s2 for the first column, 1s2p, 1s3d, 1s4f. People mess this up by changing the 1s. They would do like a 2s2p and maybe a 3s and 3d and a 4s and 4f. You don't move the principal quantum number for both orbitals. We're really just promoting one electron in these Grotrian diagrams. There are energies of those other kinds of atoms, but they're pretty high in energy because you've elevated 2 electrons, And so they would be up here in sort of this continuum area where you have a lot of different types of atoms very close to the ionization limit. So these ones that are really spread apart, these are where you've just promoted one electron, and so they're simple to understand. So that's the first four columns. The next four columns are 1s, 2s, 1s, 2p. Now you may say, well, what makes that one different than this one? Well, this is the singlet column, this is the triplet column. So in this column, it's 1s, 2p, and they're still paired. And then in this column over here, the 1s, 2p, where they're spin unpaired, either up or down, it doesn't matter. And so then the 1s, 3d, spin unpaired, and 1s, 4f, spin unpaired. So those are all 8 columns for our Grotrian diagram. Those are the lowest energy electron configurations for those excited state atoms. Okay, number 2, what anion is isoelectronic with ground state helium? So in class and in the homework problems and so on, I was always showing you cations that were isoelectronic. We were doing first ionization potential calculations and showing that we were going from a neutral to a cation. And so I wanted to extend your thinking a little bit, see how you worked your way through an anion. So that's where the analysis and application part of this problem comes in. So H minus, hydrogen anion, is isoelectronic with helium, because regular hydrogen is 1s1, and you add an extra electron there, it becomes 1s2, which is the ground state electron configuration for helium. Only it's negative because hydrogen just has one proton. So that was only worth 2 points, but again, it was something that would extend your thinking. Now it's going to be a little bit higher energy because you're putting an electron in there. It's not as stable as just normal hydrogen. And I just, again, was looking for you to use energy level diagrams to show what you might expect for that energy, and that it's more stable because of a fully filled valence shell. So if you used an sort of an energy level diagram of any sort to explain your answer, you got 1 point. And if you had this stability issue with the fully filled valence shell, that was worth another point. So that was problem number 2, pretty simple problem. If you remembered the types of electron configurations from the Grotrian diagram in class. Okay, now this one was kind of a boutique question related to one of the lectures in the notes. We looked at the expansion of the universe and using atomic spin-spin splitting or a spin-orbit splitting to know and recognize what kind of atoms were in the cloud around different stars, including our own. And that the redshift of the spin-orbit coupling, the redshift of that atomic emission could give us an idea not only of the age of that star, but also its distance from us and the rate of the expansion of the universe and so on. So these were equations really straight from class. Here's an output from the Digital Sky Survey, and there's the Z value for this particular galaxy that we have. And I asked if this was the Z value, what would be the observed wavelength of the 589 nanometer sodium line? And so that Z value is equal to the wavelength shift, or the red shift, divided by that wavelength. So the difference in observed versus actual, or measured at Earth. So this is the observed wavelength from that star. This is the wavelength measured on Earth, divided by the wavelength measured on Earth. So this ratio gives us that Z factor. And solving for lambda 0, we get 601 nanometers. So that wavelength would shift quite a bit, from 589 to 601 nanometers for this particular galaxy. A very easy line to see too as far as sodium, because it's a strong emitter. Now the next question is, how fast is this galaxy receding from us? You take this redshift and multiply by the speed of light, and it's asked for in kilometers per second. And so speed of light in kilometers per second is 10 to the 5th kilometers per second. And so we see that it's receding from us at 6,300 kilometers per second. That's what's giving us that red shift as the galaxy is receding from us and we from it. Then how far away is this galaxy in parsecs, light years, and in meters? So we have this Hubble constant, 70.4 kilometers per second per megaparsec, okay, and the velocity of the inter-object velocity is 6,300 kilometers per second. That will give us the distance of 89 megaparsecs, or 89 times 10 to the 6th parsecs. Now, a parsec is 3.26 light years, and so converting that to light years gives us 290 million light years. That's also how long it would take for that light to get to us. So at the speed of light, it would take 290 million years for light to reach us from this galaxy. That was question number 4. And then we could take that many years and convert that to distance using the speed of light. And so we have that many years and we have light traveling this fast. Converting that from years to seconds will cancel the seconds and give us distance. So putting in the normal values for days and years and hours and days and seconds and hours, we get to meters. So it's 2.7 times 10 to the 24th meters away from us. So that was option number 3. You only had to do 2 of these. So if you didn't like the expansion of the universe stuff, you could do the Grotrian diagram and the electron configurations. But either way, no matter which ones you chose, you had a healthy dose of electron configurations and some knowledge of the Grotrian diagram. Moving on to the next page, everybody in the class did this term symbol problem. No one tried the simulated spectrum, but that's okay. I'm going to assign the simulated spectrum as a homework question next. So determine the term symbols for an excited carbon atom with an electron configuration of 1s2, 2s2, 2p1, 3d1. Now in class we did the 2p2 system for carbon. So we looked at 2 electrons in the p subshell, and we looked at all the terms that came from that. It was pretty straightforward. And all I did for this problem, again, this is the evaluation and creativity section. I wanted to hit you with something that you had not seen before, but also didn't want to hit you with something that would give you 4,000 terms. So I still wanted a 2 electron system, and I wanted to add maybe 1 more unit of angular momentum. So it's pretty simple to take the carbon 2p system and move 1 of those electrons to a d orbital. So this is the system I chose. And so you can look at this. The angular momentum quantum number for this p electron is 1, and the angular momentum quantum number for the d electron is 2. So your max value is for L is 1 plus 2. Your min value is 1 minus 2, absolute value. So your min value is 1. Your maximum value is 3. So the full range of this Klebsch-Gordon series is 3, 2, 1. And the terms that are associated with that is 3 corresponds to F, 2 corresponds to D, and 1 corresponds to P. I just put these in alphabetical order over here. Well, maybe not alphabetical order, but PDF in order of their angular momentum. How about that? And then I needed to come up with the net spin for the atom. And so we could have both electrons be spin up, or we could have electron be spin up and spin down. So that's your max value. Both spin up would be 1, spin up, spin down would be 0. Calculating the multiplicity, 2s plus 1 gives us a triplet and a singlet. So these terms would have different types. We would have a triplet P and a singlet P, a triplet D and a singlet D, triplet F and a singlet F. Then for the hyperfine splitting, or the J values, for each one of these terms, and I had someone write actually on the test, this is where they ran into uncertainty. They didn't know how to calculate the J values. They were not confident in how to do that. You have to compute for each term the J values. So you have to pick the triplet P and calculate the J values. Pick the singlet P and calculate the J values. So for each term, you have a maximum of L plus S and a minimum of L minus S. So for this triplet P, because it's P, what is capital L? Okay, an S is 0, a capital P is 1, a D is 2, an F is 3. So S, P, so L is 1, and it's triplet, so S is 1. So the maximum value is going to be 2. So that first J value is 2. So triplet P2 is the maximum J value. Then you subtract 1, you've got 1, and then the minimum is L minus S. So 1 minus 1 is 0, and so the minimum value would be 0. So triplet P2, triplet P1, triplet P0. And then for the singlet P, singlet, S is 0, so L plus 0, L minus 0 is just L. And so your J value will equal your L value. And so singlet P1, because P is 1. let's think about that for the singlet D too. So that whenever you have a singlet, the J value equals your L value. And so the L value for D is 2. So a singlet D would have a J value of 2. What about a singlet F? L is equal to 3 for F, and so it would be singlet F3. Then working through these, again, D is 2, and so 2 plus 1 down to 2 minus 1. So 2 plus 1 is 3, 2 minus 1 is 1, and so they go 3, 2, 1. And then the F value, L is equal to 3. It could be plus 1, because S is 1, or it could be minus 1. So the F value plus 1 is going to be 4, 3, and L minus 1 is 2. So you have the triplet F4, triplet F3, triplet F2. So those are all of your terms for this excited carbon atom with an electron in the p orbital and an electron in the d orbital. Then moving on to the last problem, we have, again, this is the Grotrian diagram for lithium. And I went onto the Atomic Spectral Database and produced this Grotrian diagram, and I asked for all of the transitions between 400 and 700 nanometers. And it showed these 7 transitions. So these are the allowed transitions for lithium in the visible region, and I asked for you to produce a visible emission spectrum for lithium. And I said, don't worry about getting the relative intensities correct, just focus on getting the wavelengths correct. And then I even put a hint in here, the vertical axis is energy and wave numbers, so you'll have to convert the energy differences. Look at that word, differences. I even told you how to do the problem. Now I realize with test anxiety you get stress blindness and you don't actually comprehend what you're reading, but if you'll relax and focus on the text on my exams, you'll understand what to do in most cases. If you're able to use the vocabulary correctly and think about spectroscopy and what we've talked about in class. So all you have to do then is find the energy differences for this line. So coming across, that's approximately 15,000. This is set to 0. So this difference is 15,000 wave numbers. Converting that to nanometers, that's 667 nanometers. So it's pretty simple. You just take 10 to the 7 nanometers per centimeter and divide by the wave number difference between these energy levels. Doing for this one, this is also about 15,000 wave numbers, and so it's also 667. This is a little higher. I've estimated 18,000, so that's 555 nanometers. This one is about the same as this one, so that's 22,000 wave numbers, so that's 455. This energy level seems to be between these two, and so I estimated that to be 20,000 wave numbers, which gives me 500 nanometers. And then up here, this difference is a little smaller than this 15,000 difference, and so I estimated 13,000 wave numbers. Again, this is an estimate, and that gives me 770 nanometers. So these are the locations of all 7 peaks. And I have really 2 groups of peaks that are not going to be resolved. So I just drew vertical lines of the same intensity for each of these transitions, and then just for grins I put a little curve on it to kind of give the emission spectrum a line width. And because these 2 were so close together, they added together and gave me a tall peak, short peak, tall peak again because these aren't resolved, and then a short peak. So that would be a hand-drawn sketch of the visible spectrum of lithium. Now I went ahead and asked in this problem, label each peak in the spectrum with the type of transition, i.e. doublet S to doublet P, etc. So this line here is that doublet S to doublet P. So that's this line here, the 455 line dropping down. That's this doublet S to doublet P. The doublet D to doublet P, same wavelength, is this jump here. Then at 500 nanometers, we have the 20,000 wave number line. That's going doublet D to doublet P as well. This one here at 555 is this 18,000 wave number line. That's doublet S to doublet P. This one, doublet P to doublet S, is the 667 line here. Oh, doublet P, sorry. Doublet P to doublet S. Okay, that's doublet P to doublet S, so that's this line here. And then doublet D to doublet P is this one here, 667 nanometers. And then finally, the shortest difference in energy, the 13,000 wave number line, comes in at 770 nanometers. That's the doublet P to doublet S. So notice how we can label all of these transitions by their term symbols, which relate back to the Grotrian diagram, and also tell us what the electrons are doing in this emission spectrum. So that's the fourth PChem test, and hopefully this will help you study what you missed and understand kind of how I'm asking the questions that you're challenged with in our exams. So have a great day. Take care.